Hello everyone. In this segment, we'll try to understand the experimental setup of impact of jet and also one more case under the calculation of force exerted by the jet where the flat plate is hinged. So the usual way in which we'll understand the impact of jet phenomenon is this. You have a flat plate upon which you have a force, kind of a force exerted by the jet, impact of jet. This is the example for the inclined plate where inclination is theta. But when it comes to the experimental setup, we just rotate it by 90 degree. This is how we analyze. You have the plate, and vertically a nozzle is made to exert some amount of pressure on this plate. And how do we achieve the fixity here? It may be a flat plate or a hemispherical vane. The fixity is assumed by adding some weights here, by balancing this plate or a vane through a weight, and the same thing can be seen here. This is the experimental setup where you have a pipe, normal pipe, a nozzle, and the jet. Okay, and this is how a plate is fixed. Now, this plate is subjected to the movement. The moment you make the jet to form here, we balance this plate by adding some weights here, and that weight is called the actual force. And the force which we calculate using uh, the conditions of plates, probably the example like Fx equals to rho a v squared for a flat fixed plate, we call it as theoretical force, and we calculate a jet coefficient as the ratio of actual force to the theoretical force. Now, this is the example for a flat plate. This is a flat plate, and its axis is normal to the axis of the jet. So, whenever I release some amount of water in the formation of a jet here, so this is the example for hemispherical vane, where you'll have impingement of jet, and then the water releases through its ends. So, this is an example for the jet striking at the center. So in most of the cases, see, these are different types of plates and vanes, which we most often use here. You can also see the weights here, which are supposed to be added on the upper part. So in most of the cases, the aim of the laboratory setup is not to calculate force, it is to calculate the vane or the plate coefficients. And in the process to calculate velocity is calculated as discharge by area of the jet. So there are several varieties of nozzles which are used here, and the nozzle always come up with certain standard diameters like 8 mm, 10 mm. Now by using that we calculate uh, area, and uh, through the process we calculate discharge, or we observe the discharge by using something called rotameter. So rotameter is used to calculate or observe the discharges, or you can even maintain the discharge through a rotameter. So let us proceed with the other case, which is very important. And if you have a plate, if you have a straight plate, if the plate is hinged at one end, so what happens if the plate is hinged? The plate is hinged means this plate is allowed for some kind of a movement, some kind of a swing. Now this plate is hinged at one end. Let's say there is a force which is exerted. Now if you consider there is no hinge, you can calculate F equals to rho into A into V square. Now we'll see what happens once the plate is hinged and it is allowed for a swing. So the plate will travel a distance, angular distance, and that is theta, and it gets its new position somewhere here, and the inclination is theta. Now, no more this plate is called a straight plate, a flat straight plate. This plate is called inclined plate. So here we call this as F, it becomes Fn here. So the plate has its own self weight, that is W, which always acts through the center of gravity. And center of gravity is located at a distance x by 2. Let's say x is the depth, x by 2 is the distance from one hinge, or from one point, or from the hinge to the center of gravity. The same is true here. Uh, this is where Fn acts, and x by 2. Okay, so I'll draw a free body diagram here to analyze for further meaningful conditions. So the earlier dimension of a plate is this. This was the plate. X by 2 was the distance from one end to the center of gravity. The same travels an angular distance of theta, and x by 2 is this distance is x by 2, not this one. This we call it as z, and at x by 2 distance w acts, and that is Fn, which is at an angle theta with respect to the center line of the jet. So what I'll do is I'll take a moment through the hinge. I'll take moment through hinge. There are only two forces. One is Fn and the other one is W. W will create kind of a clockwise moment, and Fn will create some kind of a anti-clockwise moment. Now, if I write the moment, or if I take the moments from the hinge, it is W into x by 2 sine theta. It is W into, this is W, and we are supposed to calculate this distance, perpendicular distance. This perpendicular distance is calculated by this arrangement of a right angle triangle where one diagonal side is x by 2 and the angle is theta. So hence this becomes x by 2 sine theta. So it is W into x by 2 sine theta, which is equals to Fn into this angular distance, or the linear distance. It is Fn into the distance is Fn cos theta. It's not Fn, just Fn. Fn cos theta is this force. This is Fn cos theta. Fn cos theta. Fn cos theta, or let's say this is Fn. We resolve this, it becomes Fn cos theta. Fn cos theta into Z. So W into x by 2 sine theta, Fn is rho a v square, and cos theta. And what about this Z? Z is, by using this right angle triangle again, by using this bigger right angle triangle where z is there, x by 2 and theta. So z is x by 2 cos theta. You can cancel cos theta and cos theta here. You can also cancel x by 2, x by 2 here. So ultimately you will be remained with a simple condition saying sin theta equals to rho a v square divided by w, where w is the thing which is expressed in terms of newtons. Theta is the angle, or kind of a inclination. Rho is the density, and a is area of the jet, and v is the velocity. Okay, this is how we sort of this case, and we calculate, if at all we are interested to calculate the theta is sine inverse of rho a v square divided by w.